We put vehicle passenger occupancy detection system. Lots of passenger vehicles in urban areas, and those passenger vehicles are creating peak periods of congested traffic. Introduced dynamic traffic flow control systems in research, only minimizing the number of vehicles on road. But most vehicles have less passenger count, and road infrastructure utilization and user satisfaction based on the time spent on road, not the number of vehicles on road. So we proposed a system that can detect passenger count of a vehicle, so we can send that information to dynamic traffic flow control systems. Let's discuss about the problems we faced at the beginning. The first problem is capturing useful image streams. So this was our expectation. I just wanted to capture images of vehicles which can clearly see the passengers inside vehicles with a clear weather. But in reality, different kinds of window shading, different weather condition and lighting conditions may occur, which making the capturing difficult. The second problem is identifying passengers in captured images. So this was our expectation, simple human detection where we can see the human clearly. But in the reality, there are occluded passengers, and sometimes the portion of the passenger covered due to the window frames, and there might be passenger seats and different kinds of postures of the passengers, like seated passengers and standing passengers, which makes the image analysis difficult. So let's discuss about the system design. The system has 4 main modules, 1 hardware module and 3 software modules. First one is the camera setup. Which has near-infrared floodlight and near-infrared camera. First, it emits near-infrared light to the passengers inside vehicles. Second, near-infrared camera capturing the reflected light, and finally sending the video feed to the vehicle detector. The second module is the vehicle detector. This module is buffering video frames of single vehicle and sending buffered video frames to the frame stitcher. The third module is the frame stitcher, and its task is stitching all the frames received from the vehicle detector and produce a single image of entire vehicle and send the stitched image to the passenger detector. Finally, the passenger detector module detect the passengers in the stitched image of the entire vehicle and count the number of passengers. So let's discuss about the system implementation. First, let's discuss about the hardware module. The hardware setup had 2 components. First component is near-infrared camera. This is a normal monochrome camera without its infrared cut filter. The second component is near-infrared floodlight, and it emits near-infrared light of wavelength of 740 nanometers, so it doesn't have visual impact on drivers and passengers. So let's discuss about the software modules. The first software module is the vehicle detector. The vehicle detector was implemented using CenterNet HardNet 85 model. First, I define left margin and right margin. When a vehicle passes the left margin, the video frame buffering starts, and when vehicle passes the right margin, video buffering stops and sends the buffered video frames to the frame stitcher module. The second software module is frame stitcher, and it is implemented using video stitching techniques. First, shift features were calculated and best matching features were selected. Then all the frames were stitched together to produce one image that contains the entire vehicle. This task is challenging since the modules need to combine multiple overlapping frames. The third software module is the passenger detector, and it is implemented using efficient D7. This module detects the number of passengers using the received image from the frame stitcher module. So let's discuss about the experimental results. The first experiment is vehicle detection model selection. In this experiment, we tested on 3 models: CenterNet HardNet 85, EfficientNet D1, YOLO V4 on our dataset. And the results of this experiment showed us that CenterNet HardNet 85 has the best mean average precision, so we selected that model for vehicle detection model. Second experiment is selecting the passenger detection model. For this experiment, we used 2 models as CenterNet HardNet 85 and EfficientNet D7. Results of this experiment showed us that EfficientNet D7 is produce more accurate result, which shows on the bottom, compared to CenterNet HardNet, which showed in the top. So let's discuss about the conclusions. We need 2 camera setups for low light and bright light conditions, or we need a camera setup that can calibrate itself. Second, we cannot analyze video feeds using a single computation based model. Rather than that, we need several computation based models. Third, heuristics specific to time, location, transportation rules, vehicle physics and passenger behavior are required. Fourth and final one is heuristics are for mitigate influence of the natural phenomenon like occlusion, for example passenger occlusion and vehicle occlusion. And this will bring us to the end of this video. Thank you.